know, Professor Fay will deliver the Physics and Astronomy Colloquium tomorrow in Dane Smith Hall at 3:30, and we'll have a formal introduction then, but I'll just say a few things to introduce Alain today. As you know, I think Alain is a pioneer in experiments and foundations of quantum mechanics and quantum optics. He's going to be telling us about some of those pioneering experiments today and tomorrow. I just want to share one sort of personal story that Alain may or may not know about his influence on where I am today. So in 1988, I believe, I read an article in Scientific American about Bell's inequalities. I knew nothing about entanglement or Bell's inequalities in undergraduate, as I think that was just not typically part of any undergraduate discussion. And I was just blown away. I thought this was the most exciting thing. I actually went to graduate school to work on nonlinear dynamics and plasma physics, of all things. And I went into my friend's office. He was one of my fellow TAs, and he had a copy of this article from Scientific American sitting on his desk. And I said, Bill, oh my God, that was such a cool experiment. He said, oh yeah, Ray Chow is setting up a lab here in Berkeley to do that. I said, really? I said, that's what I want to do. And so that's how that's one of the ways that and besides reading Glauber's notes, Lesuch notes, was the reason I do what I do. So great influence, great pleasure to have you here. Welcome, Alain.
Okay, thank you very much. So, I started my career in physics in quantum optics, playing with photon and playing with light. But in 1985, Claude Cohen-Tanucci asked me to join him to start an operation on laser cooling of atoms. And as you know, it has been quite successful. And since that time, I have been playing with atoms. Your glasses are here.
He'll figure it out, yeah.
Yeah, so I am now playing with atoms that we control as well as we can. But anyway, you know, first love remains with you all your life. So a part of the activity of the lab that I have founded in the Institute of TIC, in fact, is devoted to revisiting with atoms landmarks experiments of quantum optics. And in giving this kind of talk that I'm giving today, I discovered that there are plenty of people young and even not so young who have heard of Hanbury Brown-Twiss, Hong-Ou-Mandel, but they don't know exactly what that is. So, in fact, this seminar will be a pretext. In fact, I like to teach. And this seminar will be a pretext to teach you why the Hanbury Brown-Twiss effect and why the Hong-Ou-Mandel effect are fantastic landmarks in quantum optics. And of course, I will also describe some experiment with cold atoms. So let us start. So first, this is a group which I founded, and now I'm supposed to be retired, so it's no longer my group, but it is a group that I founded. There are plenty of interested people, but the important thing is that we always consider very carefully postdoc and PhD applications. What we do in our group, quantum simulation with ultra-cold atoms, and in particular Anderson localization. We have a strong activity about Anderson localization of ultra-cold atoms, one-dimensional gases, optical lattice, long-range interactions, etc. But today I'm going to talk of this branch, which is quantum atomatics. And here you have the people who have done the last experiments on quantum atom optics. Of course, real people who do the experiment are the young people who are here, okay? Here is the old people who are not allowed to put hands on the experiment. Okay, so let us start with a general introduction. After many decades, I cannot count them, after many decades of thinking about quantum physics, I'm deeply convinced that we have two different quantum mysteries, but it's not only me. There is a guy named Richard Feynman, you may have heard of him. Okay. I think that if we read carefully, he also identifies two big quantum mysteries. In Lectures on Physics, which was published in the early 1960s, he says that wave-particle duality is the only mystery of quantum mechanics. And of course, you know what is wave-particle duality. It's the fact that what we think is a particle, like an electron, can sometimes behave as a wave, and vice versa. Something that we think is a wave, for instance light, can sometimes behave as a particle. And of course, this is very surprising, and Feynman called it the great mystery of quantum mechanics. But in 1982, Feynman acknowledged that in fact there was something else than wave-particle duality, and the something else is entanglement. And there is a clear difference. Wave-particle duality is for a single particle, while for entanglement you need at least to have two particles. And I think that indeed it's conceptually different, and I can give you my argument, the reason why I find it so different. Think of wave-particle duality. In fact, for each of these representations, either wave or particle, you have a classical description. We all know what is a wave propagating in ordinary space. We all know what is the trajectory of a classical particle in ordinary space. Of course, what is curious is that an object has both behavior, but at least this behavior, I can describe them classically. When it comes to entanglement, there is no way to describe it in our space-time. Entanglement happens in a Hilbert space, which is a tensor product of the Hilbert space describing the first particle by the one describing the other one. And basically, you have to remain in this space. And each time you make efforts to come back in our ordinary three-dimensional space, you bump into strange things like non-locality. More tomorrow in the seminar about that. So in my opinion, it's absolutely fair to make this distinction. And so this is associated with what some people, and I belong to this group, call the first quantum revolution, and this belongs to the second quantum revolution. And so today what I want to do is to present some experiments which have allowed physicists to realize the importance of entanglement. So I will start with the Hanbury Brown-Twiss effect, continue with the Hong-Ou-Mandel effect, and then describe our efforts to test Bell's inequality with atoms, because it is the subject of today, and tomorrow you will have the full Bell's inequality talk. So, the first quantum revolution is about wave particle, maybe there is no point. Okay, tomorrow we will have. Let us start with the Hanbury Brown-Twiss effect with particles. Has anyone seen a photo of Twiss already? Or is it the first time you see a photo? Everybody has seen a photo of Hanbury Brown. You type Hanbury Brown on Google Image and you have dozens of photos. But Twiss, I'm proud to have one photo. You know why there are not so many photos? He was a member of the intelligence service. And you know, these people don't publish their photo. So, Hanbury Brown and Twiss. What is the Hanbury Brown and Twiss effect? Well, it's a paper published in 1956, and it is an experiment which is described here. You have a classical source, mercury lamp, a pinhole, filter to isolate one line in the mercury spectrum, and then you will observe with a photomultiplier here, you will observe the light here, and you have a second photomultiplier, which is image of the first one in a beam splitter, okay? And so you look at the intensity of light that you have here, the current, the photocurrent is proportional to the intensity of light. This is a purely classical description, and here the current is proportional to the intensity of light that you have here. And here you have a correlator. In that time, a correlator demanded to have a motor and things like that to integrate, okay? The electronics was not much developed. But at the end, what they were looking at was a correlation function of the light and of the intensity of current, and thus of the light intensity here. This is what is called the G2 correlation function. And what they could modify was two things. First, they could change the delay here by adding length of coax. 20 centimeters of coax is 1 nanosecond. So you want to make a delay of 5 nanoseconds, you cut 5 meters of coax. I'm not joking, I've done that during my PhD thesis. The most difficult thing is to solder correctly the connector. Okay? So that's the first parameter they can change, tau, the delay. And the other parameter they can change is the position. And in fact, for convenience, rather than thinking of this position, we think of the position of the image in a beam splitter, which means that we can have the two detectors on top of each other or slightly separate them. Okay? And so this is what you get. If the two detectors are on top of each other, but you have a delay tau, if the delay tau is 0, you find that the normalized correlation function, I should have written it here, that you will understand immediately what it is, the normalized correlation function is bigger than 1. The normalized correlation function is the average of the product divided by the product of the average. So if there is no correlation, G2 equals 1. The fact that here you have something bigger than 1 means correlation. More specifically, if tau equals 0, what you have is the average of I squared divided by the square of I, which means that you have fluctuations. If there were no fluctuation, you would have a perfectly constant intensity, and G2 would be equal to 1. So there are fluctuations, and these fluctuations are characterized by this band, but when you have a delay larger than a coherence time, which is something we will define later, then there is no more correlation. If the delay is long enough, there are fluctuations which are not correlated. Same thing if you put a null delay, that we call 0, but now what you do is you separate the two detectors. Okay? And of course, if they are on top of each other, you have the same two, because this is the same signal as that one. And when you begin to separate them, then the fluctuations are less and less correlated. At one point, they are not correlated at all. Okay. It turns out that this correlation time is nothing else than the coherence, that is to say the inverse of the line width which is used. And the length that you have here is the spatial coherence, and the spatial coherence should be written here. Something has happened with my transparencies. Okay, it's here. So the length of coherence is related to the angular diameter on which you look at the source. And the reason why Hanbury Brown-Twiss have developed these ideas, that they were astronomers and they wanted to measure the angular diameter of light. And you see that by measuring this length of coherence, which is equal to lambda divided by alpha, the angular diameter of the star, you can get the alpha. If you are well educated in optics, and I have no doubt that here there are some people who are well educated in optics, you may think that this is equivalent to the Michelson-Stellar interferometer. What is a Michelson-Stellar interferometer? You have one mirror here, and you combine, so you look at a star, okay, and you combine the light, and here you observe interferent fringes, because the star is very, very small, almost a point. But anyway, it's not exactly a point, which means that if you separate enough the two mirrors which are here, then the visibility of the fringe is decayed. And it's one way of measuring the angular diameter of stars. And Michelson has done that. But there is a problem with this method. This method measures, it's an interference, measures the G1 correlation function. That is to say, the correlation function of second order in the electric field. But it is an interference. And you know, of course, that there are fluctuations of the atmosphere. And because of the fluctuation of the atmosphere, there are fluctuations in the path difference, which means that the fringes move like crazy. Michelson was a great experimentalist. He was able to watch the fringes and say visibility 50%, and then visibility 80%. It's not a joke. You can look at the paper, and he plot a curve, and he gets correctly the angular diameter. But you know, it's a method which is not so easy. And this is why. Oh, sorry for that. And this is why Hanbury Brown-Twiss developed their method, because in their method is insensitive to the fluctuation of the atmosphere. I will not explain it now, but if you ask me the question, I will explain why. But you know, there is a difference. The Michelson measurement addresses the G1 correlation function, while the G2 correlation function, it's a correlation function of the intensity, that is to say it's fourth order in the electric field. So clearly it's not the same one. Anyway, it gives the same quantity, and I'm going to explain you why. I'm going to lose my voice.
Something to drink.
I would need a microphone, but that. Let us make a classical model of what happens here. I have many, this is an incoherent source, so I have many independent emitters. And the electromagnetic field that I receive here, for instance, the electric field, is the sum of many components, but these components are incoherent, which means that I have here a random variable. So this is a sum of many independent random variables. In addition, they have the same statistical properties, so the central limit theorem applies, which means that this quantity, the electric field, is described by a Gaussian process. And as you have a Gaussian process, you know of the Wick theorem. The fourth order moment can be expressed as a function of the second order moment. And so here it translates into the fact that G2, which is fourth order, is equal to 1 plus the square of G1. And now, when you look at that, you see that indeed the width of this function and the width of that function are the same. Maybe there is a 1 of root 2 factor, we don't care. So this is why the two methods can give the coherence length of the light and thus allow you to find the angular diameter of the light. Okay. Why do I tell you that? Well, because in fact it has allowed them to really measure angular diameter of light, and you will see the discussion that it prompted. And this is an observatory that was built in Australia, in a desert. So you see here the diameter is 200 meters. It's a railway, 200 meters, and they have the detector, and they move the detector, and as soon as they separate the detector, the G2 correlation function drops. What they plot here is G2 minus 1, so it decays. Here, for instance, is 60 meters, 100 meters, and this allows them to know the angular diameter of beta of the southern cross, etc. Okay. Why do I annoy you with that? Hanbury Brown-Twiss correlation were predicted, observed, and used to measure star angular diameter 50 years ago. Why bother? Because in fact, their experiment and their proposal for experiment prompted a hot debate between people who thought that you have to describe it with classical electromagnetism, and people who say, no, we have to describe it in terms of photons. And this debate led quantum optics very far. So, is it quantum or is it classical? I remind you what I have shown, but in a simpler way. From a classical point of view, at the end of the day, the Hanbury Brown-Twiss bond is nothing else than the fact that the square of the intensity averaged is bigger than or equal to the square of the average. Okay? And for a Gaussian process, you have a factor of 2. So it's totally classical. Okay. Oh, by the way, without coming to the interference, I like to give this interpretation, which I think is illuminating. Let's suppose that here you take a photo, you freeze the pattern of intensity at the scale of 1 femtosecond. at that scale, all the various waves interfere with each other. Of course, it's a random interference, but they do interfere. It's called a speckle. A speckle is what you get if you pass a laser beam through. Can you see on the side? You pass a laser beam through a piece of plastic, for instance, that scatters light, and you have black and bright spots, black spots, etc. So at the scale of 1 femtosecond, this is what you have. But now if you let time go, then it begins to change, and if the two detectors are in the same grain of speckle, you have correlation. If they are separated by more than one grain of speckle, it's uncorrelated. This way of seeing this experiment is extremely fruitful, believe me. Okay, let us continue on about the discussion between classical and quantum. If you try to describe this experiment from a quantum point of view, so you say now I'm doing photon detection. So I have two detectors which work in the regime of photon counting. And the G2 function is nothing else than the ratio of the probability of joint detection of two photons. Two photons are detected simultaneously, so it's a coincidence between the two photons, or with a delay tau, divided by the product of the single detection probabilities. So this experiment, from a point of view of quantum optics, and if you work in the photon counting regime, is G2 is equal to that. And now if you find G2 equal to, it means that the photons tend to come together. And this renders some people crazy. They say, it's not possible. You have a star. The star is emitting photons, okay? Obviously, they are totally random. So there is no reason that they like to be bunched, because this, if you have a factor of 2, it means bunching. So if you had independent detection events, you would have 1. But if you have 2, the probability to find 2 photons at the same place and at the same time is larger than the product of simple probabilities. This is bunching. But how might independent particles be bunched? This was the question which really puzzled many people. Now, Mr. Hanbury Brown-Twiss were astronomers. They needed money to build their experiment. And you know, it was a strange time, 60 years ago. When you needed money, you had to file an application. And you had to face stupid referees. And the referees say, no, this totally idiot cannot work. It's clear that the photons are independent. So they did not get the money. So they did their best to reply to the referee. And the first thing they did was a small experiment I have described, a tabletop experiment. So they did the tabletop experiment, and then they began to argue that, yes, light is made of photon, but after all, it's also wave and particle. And they began to argue, but they do not convince the referee. And it's a pity, because in fact, when they analyzed this formula, they correctly identify the two terms. The first term is a term which is associated to particle randomly distributed, what we call shot noise in modern language. And the second term is a term that you associate to waves. You have bit knots between various waves, and if these various waves are incoherent, a small calculation shows that it is a term that you get. So they say, look, this is a shot noise, this is the waves, and so it's not as simple as just saying that it is independent particles. And at this point, I like to make a comment. You know who demonstrated this formula first and who interpreted it first? Any idea?
Einstein.
He knows. Einstein, 1909, the so-called Salzburg Conference. In that conference, you know, Einstein in 1905 introduced the concept of least quantum photon. Okay? But of course, Einstein knew that many optical phenomena have to be described by waves, and he was obsessed by that. And in 1909, in the famous conference in Salzburg, it was a conference of the German Physical Society, although it was in Austria and it was not yet the Anschluss, but okay. He gave this talk, and in this talk he was able to make the calculation of the fluctuation of black body radiation. And he found this formula expressed in his words, and he correctly identified this as, he said, this is what we would have if light was made of particles. This is what we would have if light was made of waves, incoherent waves, and because we have the sum of the two, light is both a wave and a particle. I insist, 1909. Unbelievable. Okay. But coming back to Hanbury Brown-Twiss, the reaction of the referee were so bad that they immigrated to Australia. It's not a joke. Well, so this is a comment about Einstein, it's in the reverse order. By the way, talking of Einstein, if you don't know this book, buy this book. Douglas Stone, Einstein and the Quantum. Anybody who buys this book and is not happy with the book, I reimburse it. No, I'm not joking. I know that you are not going to ask for reimbursement. It's so good. It explains the role of Einstein in the emergence of quantum mechanics. Let us go back to Australia. They immigrated to Australia, and you know, in Australia they had money and they could build, they have been shuffled in my transparency, and they could build the observatory. Now, are there Australian people in the audience? Raise your hands. Okay. So I'm going to be, yes, I'm going to be careful. There are two interpretations of the fact that in Australia they were welcome. The first interpretation, which is not good, is to say that the Australian people did not know yet about the photons. The second interpretation is that the Australian people are smarter than the British people. Should make your choice. It's duality, yes. Okay. Now, anyway, even with this argument that light is both a wave and a particle, to be honest, when you look at all the explanation, it's not really convincing. When you read this, they had a good intuition, Hanbury Brown-Twiss, and of course their classical description is perfect, but when they discussed in terms of quantum physics, it was not fully convincing. And the first fully convincing explanation for the Hanbury Brown-Twiss effect was given by Fanon, but Fanon, it's a paper that nobody can understand. I will give you the reference, read it, and you read the book. It's impossible to understand. But the ideas were there. Glauben gave a model which is crystal clear and which allows to really understand what happens from the point of view of quantum physics if you insist on describing the Hanbury Brown-Twiss effect with photons. And the model is the following. You have two detectors which are excited. Two atoms, two emitters which are excited, and two detectors waiting. And then at the end of the process, you have a joint detection. That is to say, the two detectors are excited, and of course the two emitters have emitted the photons. They are in the ground state. And you want to calculate, from a quantum point of view, the probability of this process, of this emission and this detection. And you notice that there are two paths to go from here to there. In the first path, the photon emitted here is detected here, and the photon emitted here is detected here. And I describe it by this diagram. But you can also have this photon detected there, and that photon detected there. And at the end, you cannot make the difference. And when you have two paths, which are indistinguishable, you must add the amplitudes. And when you add the amplitude, you have an interference. And this interference can be constructive or destructive and creates fluctuation. And this fluctuation, when you add all of them, you get the factor of 2, which is a Gaussian factor of 2. So, why is it important? Because to my knowledge, for the first time, somebody invokes two photon interference effect. It's not an ordinary interference. It's an interference between the amplitude of the two photons. Is when I told you We have a calculation in a Hilbert space. These amplitudes are in a Hilbert space. They are not in our space. It's not two waves interfering in our space. It's interference between abstract amplitude. So in fact, to my knowledge, it was for the first time invoking such two-photon interference, and it was a quantum weirdness associated with the second quantum revolution. Another comment here. When we describe it like that, of course we get a bunching effect, but this bunching effect, the fact that the two photons like to be detected on top of each other, is not related to an attraction. There is no interaction energy between the photons, okay? There is no attraction. It really results from this abstract process. And at this point, I cannot avoid citing again Einstein. Not exactly about the same problem, but very close. When Einstein published in 1924 his paper on what is called Bose-Einstein condensation, okay? Schrödinger sent him a letter. They say, I have read your paper. I think you have made a mistake in the way you count the various possibilities. Okay? And Einstein replies, no. I admit that the way I count the probability is different from the way we use habitually, but in fact it's because the particles are undistinguishable, and then if you can look in this letter is reproduced, okay, you can find the letter. Einstein makes the drawing where you have two boxes and two balls. And he says, how many possibilities to distribute the two balls in the two boxes? If you can distinguish between them, there are four possibilities. This, that, this, and that. Four. But if they are indistinguishable, you have this, that, and that, period. Which means that the probability to have the two balls in this box is 1/3 rather than 1/4, and the possibility to have here 2 is 1/3 rather than 1/4. And so Einstein concludes, you see, with this way of counting, these particles tend to like to be together. And he goes on, he says, but there is no real interaction. It's the way we count it which make it look like they like to be together. It's exactly the same thing as with the Hanbury Brown-Twiss effect. The photons are not attracted towards each other. Anyway, when we detect them, they like to be detected together. I think it's a great mystery. So there was a furious debate about that, and when the laser arrived, the debate was even stronger, because there were people who say, oh, with a laser it will be very easy to observe the Hanbury Brown-Twiss effect, and Glauber said, no way to observe the Hanbury Brown-Twiss effect with a laser. And there was an experiment done by Arecki in 1966, where he compared the measurement of the Hanbury Brown-Twiss effect with chaotic light. You have the bump here, and then he switches to a single mode laser, and with a single mode laser, there is no Hanbury Brown-Twiss effect. So Glauber was right. And I don't say it was wrong. You know.
I do.
And there is a very simple classical interpretation. You know that in an almost perfect laser, the reason why you have a line width is the diffusion of the phase, but basically there is no fluctuation of the amplitude. So if you take the square modulus, the intensity is constant, and if the intensity is constant, G2 equal 1. Of course, you can also make a full complicated quantum calculation. It's equivalent to that. Okay. So the Hanbury Brown-Twiss effect was a landmark in quantum optics, but if we look at it, it's really trivial to understand it if light is described as random electromagnetic waves. But its subtle quantum effect is light is described by made of particles, of photons, okay? So it's an intriguing quantum effect for particles. So now we are working with atoms, so we are going to look into the Hanbury Brown-Twiss effect with atoms. But I must say that there is a beautiful paper by Gordon Bain, which was published in Acta Physica Polonica. I doubt that you have that in your library, but in fact you can find it on archive. Okay, so, and in this paper, Gordon Bain explains that people in nuclear physics observing collision between nuclei and using the Hanbury Brown-Twiss effect, can measure the cross-section just like astronomers measure the angular diameter of stars. Isn't that cool? Okay. Let us come to Hanbury Brown-Twiss with atoms. I must first say that the pioneers in that was Shimizu and one of his collaborators. In 1996, he made an he carried out an experiment which was a fantastic tour de force. He had a trapped cold neon, dropped them here, had detectors, and accumulating data for hours and hours and hours. Finally, he obtained the bump of the Hanbury Brown-Twiss effect, and it was, when you analyze this experiment, it's really very similar to the original experiment. But it's so difficult that you are not going to repeat the experiment and change the parameters. So we embarked into experiments in our lab, experiments using metastable helium. Metastable helium is really the workhorse of our experiments on quantum atom optics. Why is it good? Everybody knows that helium has 2 electrons. And everybody knows that there are 2 different types of atomic levels. Levels where the 2 electrons have parallel spin, and levels where the electrons have antiparallel spin. For antiparallel spin, it's S equals 0, it's a singlet state. But for parallel spins, it's S equals 1, it's a triplet state. You can have 1, 0, minus 1. And helium being a quite simple atom, you have selection rules which are extremely strict, which tell you that by absorbing light or emitting light, you cannot go from a triplet state to a singlet state. Which means that if you start with an atom of helium in a triplet state, by absorbing or emitting light, you will bump into the lowest triplet state, which is here. So for all practical purposes, if you want to manipulate this atom with light, so you want to decelerate it, cool it, trap it with light, for all practical purposes, this acts as a ground level. And you can operate on this resonance transition at 1.08 micron, and we have laser for that. And so the only difficulty of the experiment is to excite the atom to a triplet state, any triplet state, by electron bombardment, and then you shine laser on it and you can manipulate, decelerate, stop, trap, etc. But on the other hand, we should not forget that the real ground state, which is a singlet state, is here, and there is 20 electron volt difference. Now, when a metastable helium atom arrives close to a piece of matter, then it can decay to the ground state, releasing 20 electron volt of energy. And 20 electron volt is much more than necessary to ionize anything. For instance, typical work to extract an electron from a piece of metal is a few electron volt, okay? And so when your atom will arrive on a piece of metal, it will eject an electron. This is exactly similar to the photoelectric effect, which means that if now you have an electron multiplier, you can play with it like pioneers of quantum optics, have played with the photoelectric effect. Okay? Maybe you want to know why, when it comes close to a piece of matter, it can decay. Well, there is a very simple hand-waving explanation, which is the following. When you come close to a piece of matter, you have a van der Waals force. Van der Waals force is an electrostatic field, but the electron is very fast in the electrostatic field, and you have a motional magnetic field which can flip one of the spins. Well, it's not rigorous, but that's the way I understand it, and I'm happy with it. Okay. So now you have this metastable helium atom, and you can play with it because you can detect it individually. And this is an artist's view, that is to say, one of our students have done this view. Here you have a cloud of trapped metastable helium atom, some drop, and when they arrive here on a piece of metal, boom, there is an electron which is emitted. In fact, it's not an ordinary piece of metal. is what is called a microchannel plate. A microchannel plate is millions of small tubes. Each tube is an electron multiplier. You apply 2 kilovolts between the upper face and the lower face of these. You have many tubes, and when the electron arrives here, you have an electron multiplier, and on the other side, you have a macroscopic pulse that you can treat with ordinary electronics. So it's really just like a photomultiplier. In fact, it's even better. Because what we have done, we have used delay lines that we put below here. And so when you have an atom arriving here, on the other side you have a pulse of electrons, okay? But these will be split, and by looking at the difference in the time of arrival at the various ends of the delay line, you can see where the atom was detected. And now you have a detector which can detect single atoms and say where it is detected. So you have a two-dimensional detector, but it's even better. It's a three-dimensional detector, at least the way we use it. Why? Because if you look again at this figure, you have cold atoms, you drop them here, basically they have all the same velocity. So the time of detection gives you the third dimension, and in fact you receive a cloud of atoms and you can reconstruct the full distribution in 3 dimensions. It's a fantastic system. Okay, so with this, we have done an experiment which is almost the Hanbury Brown-Twiss experiment. It consists of having a cloud of atoms. They are cold, but anyway it's a thermal cloud, and you let them drop. And as I said, you reconstruct the distribution of the various positions. And you build the histogram, number of pairs, as a function of a vector joining the two positions. And you get essentially 0 plus some noise. So you repeat the experiment, you get again 0 plus some noise. You repeat 1,000 times, and then you average the various correlations that you have measured, and then the miracle happens, you get here above. Now we have repeated the experiment with helium-3. Helium-3 is a fermion. And when you have a fermion, you remember when I told you you must add the two diagrams. Well, why adding? Why not subtracting? Well, for boson you must add, and for fermions you must subtract. And so, for fermion, for helium-3, which is a fermion, you have a dip rather than a bump. Well, in fact, there is nothing else than the Pauli exclusion principle. But you see it directly from this diagram, etc. So, here, clearly, because we have particles, we have interference of two atom amplitudes. And the sign depends on the quantum statistics. And by the way, Ivan, you know almost everything. Do you know why the width here is different from the width there? I give you a hint. Helium-3 and helium-4 have different masses, so they don't fall the same way.
So the coherence.
Nobody is shocked? There is no Italian guy who knows Galileo? When I say that helium-3 and helium-4 do not fall the same way, it sounds stupid. It's not totally stupid. If I consider the de Broglie wavelength, they have the same velocity, but the de Broglie wavelengths are different because the masses are different. And the de Broglie wavelength of helium-3 is bigger than the de Broglie wavelength of helium-4 for the same fall. And this is why I have something wider. Interesting. Okay, let us conclude. The conclusion is that both effects, when looked at from the point of view of quantum physics, are really effects where you have to add two particle amplitude. But it seems to me that with fermions, the effect is yet more quantum. Because when you have the boson, you can interpret it with wave, and after all, when you have the bosons, if rather than thinking of light intensity, you think of density of particles, what you have is nothing else that the average of the square of the density is bigger than the square of the average of the density. But when you have fermions, what you have to face is the fact that the square of the density average is smaller than the average of the square. This is surprising, isn't it? This cannot be true. Cannot be true with ordinary numbers. But if you replace this by a dagger A, if you introduce creation and annihilation operators, then this becomes true. So in this sense, I think that the Hanbury Brown-Twiss with fermion is really more quantum, because it demands explicitly second quantization and quantum statistics. Okay, let us continue. So here you have the title. This is Mr. Mandel. Hong-Ou-Mandel effect. This is an experiment which was published in 1987. If you find it a little too complicated, in fact, this experiment amounts to doing this. You have here an ultraviolet photon which is split into parametric down conversion, and you recombine these two photons, which are emitted simultaneously, you recombine them on a beam splitter. And you look at the probability of a joint detection simultaneously for them. And what you can do is change the position of this beam splitter so that in the middle the two paths are exactly equal, but if you push one side on the other side, the two paths are not exactly equal. And this is what they observe. When the paths are exactly equal, they find zero, which means that when the two paths are exactly equal, the probability of joint detection is zero, which means that the two particles arrive on the beam splitter, but they will be detected either both on one side or both on the other side, but never one on one side and one on the other side. When you read their paper, they were extremely happy because it allowed them to measure the width of that dip with an accuracy of femtosecond, although they did not have electronic that fast. So it was very smart because by looking at the position of the beam splitter, they could control the femtosecond. But what is amusing is that in this first paper, they did not realize what was the reason why this paper is still cited and had been cited thousands of times. 1 year later, they say, by the way, what we published last year is a very interesting quantum effect. And now I am going to explain you the quantum effect. How can we understand this surprising fact that you have one particle arriving here, one particle arriving here, but you will never observe simultaneously here and there? The interpretation is the following. Again, two paths to go from an initial situation to a final situation. Initial situation, the two particles are emitted. Final situation, the particle emitted towards up, in the upper direction, is reflected here and detected here, and the one emitted downwards is detected here. Second possibility, the upper particle is detected down, and the lower particle is detected up. And now, if there are here some young people who think that when the professor insists that on a beam split there is a factor of pi somewhere, and that this factor of pi is very important, here you have the effect of this factor of pi. You know that when you have a beam splitter, if you reflect on one side, you have a dephasing. If you reflect on the other side, you have the same dephasing plus pi or minus pi. And this is not a technical issue, it's a fundamental issue. If this pi was not there, you would not have conservation of energy in the beam splitter. So it's very fundamental. And here, you have two reflections, so there is a pi, whatever side it is, there is a pi, while here you have two transmission and there is no pi. So this amplitude and this amplitude have just a minus sign. There is a pi difference between them. And because there is this pi difference, when you add the two, you have zero. This is what is written here. So this is a spectacular evidence of two-photon interference. And here, in contrast with the Hanbury Brown-Twiss with light, there is absolutely no way to interpret it with classical waves. And I give you a flavor of the demonstration. Let's suppose you have two classical waves arriving here. If they are mutually coherent, by playing with the relative phase, you can convince all light to go here, or all light to go there, or anything in between. But remember that in your experiment there is a randomness. So you want also to have randomness. So you must take this phase between the two coherent beams random. And when you randomize it, you still have a dip, but the dip never goes below 50%. So if you observe something below 50%, it cannot be classical waves. So in contrast to the Hanbury Brown-Twiss effect, there is no way to describe that by classical waves, and even less with classical particles. Okay. So this what we have, interference between two photon amplitudes. But if you want to look at the state which is produced here, it's a two photon entangled state, 2, 0 plus 0, 2, 2, 0 plus 0, 2. It's what is called the noon state. So it's really entangled. Now, a remark in passing. In the experiment that I have described, the two particles are produced in the same source. But in fact, if you work out carefully what happens here, nobody demands that the two photons have been emitted at the same place. You can take the two photons emitted in different sources, different galaxies, different stars, or for Bloès and Granger, different atoms hold in two different optical tweezers. And if you select modes which are exactly image of each other on a beam splitter, and in addition, if you are lucky enough that the two photons are emitted at the same time, then you have the Hong-Ou-Mandel effect. Because this state is due to the symmetrization that you have in the quantum statistics. And this symmetrization is always necessary, even when the particles have not been produced at the same place. So, okay. Now, can we observe the Hong-Ou-Mandel effect with atoms? Yes, we have done it. And this allows me to explain progress in the technique we are using in our quest for reproducing quantum optics with atoms. What we need is to produce atoms from the same position, because it makes life easier to have Hong-Ou-Mandel effect, because they are automatically produced together. And for that, we use the fact that Bose-Einstein condensate have some interaction energy. So when we are going to collide two Bose-Einstein condensate, here, one going to the left, one going to the right, there is interaction energy, which means interaction energy means collision. But anyway, from this point of view, it's better to consider, when you look carefully at the equation, the Bloch-Pitayevsky equation, you find that when it collides, you have a term of interaction which is exactly the same as a chi3 in nonlinear optics. And so, in fact, you have a process which can be understood as four-wave mixing. So you have two big pumps, and you get two small waves like that. So the idea is that when you collide the two Bose-Einstein condensate, then you can get pairs of atoms like that or like that, okay? And if the velocity are the same, you have constraint on momentum energy, etc. So this is how we do the experiment. We take a Bose-Einstein condensate, and we push half of it in one direction, half of it the other direction, by laser, okay, radiation pressure, etc. And we observe, and then we let everything fall, and we observe what happens. So you have a cloud which passes through the detector, and then at the end, and the sphere has passed. And we can register everything, and when we register everything, this is what we observe. So this is the distribution that we observe in 3 dimensions. And because you cannot see easily in 3 dimensions, I'm going to turn it, to rotate it. Well, my student have done the program, but this is really what has been observed. And you see, here you have really a shell, and all the atoms are on a shell. The big blobs which are here is we are working in the perturbative regime. So the 2 big Bose-Einstein condensates continue. Only a small fraction of the atoms are like that. And this is due to equation of polarization. Don't look at it. The important point is that most of the atoms are distributed here. And now, of course, the question is, okay, they are distributed here, but do we have pairs? And this is the beauty of this technique. Once we have recorded everything in the computer, we can quickly look at whatever signal we want. And so it takes some time, but looking at the correlation between atoms which are on antipodes of each other, indeed, there is a correlation. There is a correlation. So we prove that we emit atoms in pairs. So we are in a good position to do the experiment which demanded pairs of photons, and now we have pairs of atoms. Anyway, there is another problem. With this process, the pairs are emitted in all the directions in space. And in fact, it's very complicated. You can catch only a small solid angle. So you are going to have a very small signal. The strength of nonlinear optics is that you have something which is called phase matching. Phase matching is the fact that when you combine 2 waves, the third wave is forced to go in a certain direction because you have conservation of, let's say, momentum and energy. And here, well, we don't have something like that. So is there a way to have a phase matching? And the answer is yes. There was a wonderful suggestion by Muller and Ellingser in 2005. And the suggestion is the following. First, you force the atoms to circulate along a well-defined direction. So you have what is called an optical tweezer, that is to say a laser beam which attracts the atom towards the center of the beam. So it becomes a one-dimensional problem. Second, on this one-dimensional problem, you impose a periodic potential with a standing wave which creates a periodic potential. And now you have the standard problem of a quantum particle in a periodic potential, that is to say the solution is block waves, and this is a dispersion of the block waves. Now, the process of production of pairs, which is sometimes described as dynamical instability, can be understood at the fact that in the Bose-Einstein condensate, which is here, you have 2 atoms which collide and which are going to be emitted. And in this process, you want to have conservation of energy and of quasi-momentum. And when you look at this dispersion relation, if, for instance, you have the Bose-Einstein condensate which has a velocity which is here, this velocity and this energy, so dispersion, well, when I say velocity, I mean k vector, the same thing. Okay? When you have a Bose-Einstein condensate with a given velocity, that is to say a given k vector, if you want to eject 2 atoms conserving energy and quasi-momentum, there is only one solution, that is this one and this one. Which means that now, if my Bose-Einstein condensate has a well-defined velocity referred to the standing wave, I have 2 waves, 2 ejected atoms with a well-given direction and a given direction and a given momentum. So I have the phase matching condition. Here is a paper that we published in proving that indeed by turning a knob, it's a complicated knob, but by turning a knob, we can obtain 2 atoms with this velocity or this velocity or this velocity. So now we have our pairs of atoms emitted in well-defined direction of space and with well-defined velocity. So with this is the experiment we have done. So here we have the situation with the Bose-Einstein condensate and the standing wave. And And rather than moving the Bose-Einstein condensate, we move the standing wave, the same thing. Okay? And choosing the velocity, we produce two atoms with two velocities. They are both going in the other direction, but with different velocity. And so they are going to do parabola like that. And it's not so easy to look here, so I put myself in the free-falling frame of reference, that is to say a frame of reference which is in the center of gravity, center of mass of the two particles. So now I am here, one particle goes upwards, one particle goes downwards, okay, in this frame of reference. Now here, at this point, I apply another standing wave, and I do Bragg diffraction. This standing wave is moving exactly at the mean velocity, that is to say it is fixed, and I have Bragg diffraction so that this is reflected landwards and that is reflected upwards. So now I have two mirrors, I recombine my two particles. And here I'm going to apply again the same Bragg effect, the same standing wave, but I will apply it for half the time. So rather than being a pi pulse, it's a pi over 2 pulse. And now this is a beam splitter, and I recombine the two things. So you see, it's exactly the same scheme as the Hong-Ou-Mandel scheme, with a difference. In nonlinear optics, they put some pinholes to select the direction. We don't select anything. We record everything. It will be important at the end of the talk. We record everything, and we make an a posteriori, we select the modes which are well matched to each other, and once we do that and we look at the correlation, we indeed obtain the dip of the Hong-Ou-Mandel, and the dip is below 50%. Well, this is amusing. What does it tell, below 50%? It cannot be understood as an ordinary interference between the Broglie waves. But I am serious. Ordinary interference between the Broglie waves would be in our space. Here it has to be understood as an interference between two atom amplitudes in an abstract Hilbert space. Okay, let us continue. So, okay, blah, blah, blah. Now, as Ivan said, I started working on Bell's inequality long ago. And when I think about the Hong-Ou-Mandel experiment, it's an absolutely fantastic quantum effect, but anyway, it's clearly not as quantum as violation of Bell's inequality. And it took me a long time to understand why. And first, I have an indication that it is not as quantum. I can build a local hidden variable model for the Hong-Ou-Mandel, and I cannot build a local hidden variable model for violation of Bell's inequality. You will see that tomorrow. So this tells me that Bell is more quantum than the Hong-Ou-Mandel. And it took me a long time to understand why. The reason is that here I have entanglement. I have entanglement between two particles, but I have entanglement between two particles only in two modes. Here I have only two modes, this mode and that mode. While in a Bell's inequality experiment, look at this, you are going to see that tomorrow for 1 hour, okay? So here the state which I produce is the superposition of two photons with polarization like that, and the same two photons with polarization like that. Now I have 4 modes, 2 modes on one side, 2 modes on the other side. And this is absolutely necessary for a violation of Bell's inequality, because you want to be able to have different observables here, different observables that do not commute. This is why you need 2 modes on each side, that is 4. Okay, so looking again at our experiment with that produces the Hong-Ou-Mandel effect, we understood that in fact maybe there is more than we thought in the data. And at this point, it is important that everything was recorded in the computer, because we thought of that later. And actually, it's a PhD student who thought of that. It's not the boss. So it's important to have good PhD students, as you know. So let us consider again the scheme by which we produce our pairs. I told you the velocity or the momentum of the pair are obtained by two constraints: conservation of energy and conservation of momentum, well, quasi-momentum. In fact, it's not totally true. Conservation of quasi-momentum, yes, but conservation of energy, not really, because it's pulsed. And it's pulsed in a short amount of time, and so you have a dispersion in energy. So in fact, it means that, yes, we have produced a pair with P naught and minus P naught, but in fact, we have simultaneously produced a pair P prime and minus P prime. P prime and minus P prime because the conservation of quasi-momentum is serious, but you know it's a different energy. The kinetic energy is different, but it's allowed. And indeed, when you look, so you do your experiment and you look the atoms falling on your detector, and you plot the distribution of velocity, and indeed there is a blob here and a blob there. It does not tell you that there is correlation between here and there, but remember, everything has been recorded. So you can observe, when I observe this, what did I observe? I observed the other guy here. And you can plot here the correlation between detection here and there, and indeed they are produced by pair like that, like that, like that. So now we have more than 2 modes. We have several modes. And in fact, something absolutely fantastic happens. This was the experiment as it was designed. You have here the Bragg reflection which makes a mirror, and here the same Bragg reflection that makes the beam split. In fact, you discover that with the same standing wave, you could as well play with this pair or with that pair, and if it happens by chance that you have this relation between the momenta, you are going to recombine 2 modes here and 2 modes there. And now you have a scheme with 4 modes. So, in principle, you are in a situation to test Bell's inequality. But there is a problem. To test Bell's inequality, you must be able to change separately the dephasing that you have here and the dephasing that you have there. But we did not plan to do this experiment. So it is what it is. We cannot change it. Fortunately, there is an effect which is called the Doppler effect, which makes a different dephasing for these and for other situations. And eventually, by digging into all the data, the students were able to identify 3 sets of data, 3 sets of data, independent of each other, corresponding to various dephasing. We did not control the dephasing, but the dephasing were there, and they were different. This is the first set of data. We have the P++, P minus, etc., and the correlation coefficient is here. This is 0. If you find something here, there is no correlation. There is correlation. One standard deviation, but there is correlation. Here, it's 0. And here, we have some correlation. And when we calculate the dephasing due to the Doppler effect, it makes sense. Here, dephasing is 0. Here, we have dephasing. Here, we have dephasing. So with this, what do we conclude? Well, we do not want to push too far for 2 reasons. The first is that we are very honest. And the second is that one day we are going to do the real experiment in which we really control the phases. So, in our paper, what we have concluded is that our results are consistent with the fact that we have an entangled state, but to make a stronger claim, we need an experiment where we can vary at will the various phases. What do I mean by our results are consistent with that entangled state? The debate is the following. When we create P minus P and P prime minus P prime, is it a mixture? And in that case, there would be no correlation? Or is it like that, a linear superposition, and then we have something, a correlation which is different from zero? We think that it is enough different from zero to say that it cannot be a mixture. It is better than a mixture. We don't say that it is a pure state, but it is better than a mixture. Okay, so with this, I think that I will conclude just in reminding what were the main landmarks in optics of light and optics of atoms. 19th century interference, Young and Freeman. Interference of atoms were demonstrated in 1990. Production of single photon started in the 70s and the 80s. Production of single atoms 2002. Photon correlation, Hanbury Brown-Twiss, 1955. Atom correlation, Hanbury Brown-Twiss, 2005. Production of pair. For photon, it's a chi2. For atoms, it's a chi3, but this is a technical detail. It's a nonlinear effect. Observing squeezing. I did not show it, but we also have squeezing with our production of atoms. Test with atoms produced by a radiative cascade. There is nothing equivalent with atoms. What would be the equivalent for atom? It would be a molecule which is dissociated in two atoms, and there is a correlation between the internal state of the atom. This has not been observed. Hong-Ou-Mandel, and what is left to do, test of Bell's inequality with atoms, and we are going to do this test, and the idea, along what I have shown here, is something which was shown with photon by Rarity and Tapster. So again, we create P3 minus P3 plus P4 minus P4, where I don't know what I did, but you see what I mean. This superposition here, and the idea is really to control the phase, to demonstrate that we have entanglement. Why do I think that it is interesting? Well, first, it's fun, you know, testing Bell's inequality. I started my career testing Bell's inequality, finishing it with another test of Bell's inequality with atom would be fun, but maybe you are not interested by that. There is a more important argument. If we succeed in this experiment, it will be the first experiment in which we demonstrate entanglement between external degrees of freedom, mechanical degrees of freedom involving the mass. And maybe this is touching upon the frontier between gravitation and quantum mechanics. I say maybe, okay? I doubt that with helium atoms, which are light, we touch very much. But anyway, there is no experiment, to my knowledge, in which people have used massive particles and they have entangled external degrees of freedom, I mean either position or momentum. And so it would be the first experiment involving entanglement of momentum, so I think it's worth doing it, and we are trying to do it. But it's a very difficult experiment. And with this, I think that it is the right time to thank you for your attention. And you can ask me as many questions as you want.
All right, you heard it here.
Until the moment when I have no more voice.
So, what about the entanglement? So people have claimed to measure APR, Bell's inequality with B0 bar mixing, B mesons.
Ah,
And,
No, we
it's a
speak-
little controversial as to whether they actually measured a legit Bell's inequality.
I doubt that they have demonstrated entanglement with PP bar, but I doubt that they claim Bell's inequality, or maybe I don't know the
There was a
literature.
paper that came out where they claimed.
Okay, so maybe, but I doubt that it is a clear-cut experiment.
That's true.
Oh, that's true.
No, it wasn't clear. It was controversial.
It was controversial, yes.
The actual
Okay.
Bell's
Yeah.
inequality maybe was.
The problem, I discussed this, what is the name of the American physicist who got the Nobel Prize for Cashot, Calum? I discussed this with him. what is that? Well, you know the field, you know better than me. Anyway, I discussed with him. It's clear that this K short, K long is an example of entanglement. But anyway, to perform a Bell's inequality test on it is quite difficult. One of the problems, when you want to perform a test of Bell's inequality, as I explained at the end, the ideal situation is a situation in which you have two modes on one side, and you are able to make different combinations of these two modes which are associated with observables that do not commute. And I think that this was a problem, to build the correct observables, if I remember well. But I would not argue that, okay, if somebody has done an experiment like that, fine, let us cite it. But here, we hope to have a real test of Bell's inequality in which we turn a knob. This knob is a phase. By changing the phase, we change the observable, and we test at the magic angle of Bell, which are 22.5 degrees and 77.5 degrees. More tomorrow. Other questions? Nobody want to know why there is no fluctuation? Why the atmospheric fluctuation are not relevant in Hanbury Brown-Twiss?
Sure.
So you said that there is a, in your experiment you can do, or you are planning to do a Bell's inequality in the external degree of freedom.
Yes.
Is there a way, have you other degrees of freedom, for example, internal?
Oh yes, yes, but I don't want to repeat an experiment with internal degree of freedom. Weyland has done an experiment in which he has shown Bell's inequality with internal degrees of freedom of iron. You can argue that iron have a mass, but it does an experiment with internal degree of freedom. So the mass is not really relevant. I want an experiment in which the mass is relevant. And this is why I want to entangle P.
So how do you deal with, what are your outcomes? You have continuous variables here, so what kind, I forget the rarity caps there.
It's not continuous variable.
Okay.
We select two modes.
Okay. So what are the outcomes here? Is whether it comes in one mode or the other?
No.
I forget the rarity experiment from back. Yeah.
Here, you select modes, so you make it a two-mode problem.
Mm-hmm.
Because you put pinholes, okay? And the outcome is plus here and minus here.
Which is which mode it comes in.
Yeah.
Yeah.
I'm really losing my voice.
Oh, sorry. Maybe the questions will go forever, but we'll see. Questions.
So, Hanbury Brown-Twiss atmospheric fluctuation.
Yes.
No, but I think it's so smart. In Hanbury Brown-Twiss, you look at fluctuation on one detector and fluctuation on the other one. Fluctuation on one detector comes from a bit note which is in the gigahertz range. So you associate with it a wavelength which is of the order of a few centimeters. And the fluctuation of the atmosphere does not make a change of a few centimeters in the optical path. It makes a change of a few micrometers. So for Michelson, the micrometer is important. But for Hanbury Brown-Twiss, it's not important. After saying so good things about Hanbury Brown-Twiss, I have to say something which is very sad. It's no longer used for the following reason. When you have a star, it's, let's say, white light, broad spectrum. But if you try to do Hanbury Brown-Twiss with a broad spectrum, the bump would have a width of a few femtoseconds. And no detector is able to follow on a few femtoseconds. So you need to put an interference filter to reduce the spectrum of the light that you observe. So you lose many, many photons. And for this reason, Hanbury Brown-Twiss has been used only for the brightest stars that you have in the sun. And if you now you understand why people develop this interferometric scheme with various telescopes in Chile, because it amounts of repeating in a more sophisticated way the Michelson experiment. When you look at the G1 function, it's the electric field, and then you can use a full spectrum. But with Hanbury Brown-Twiss, you have to select a small part of the spectrum, so it's not efficient. It's interesting. It's not really quantum optics, but it's interesting anyway.
Any questions from Los Alamos?
No, we are disgusted. No question? No, no question?
So, I just wanted to add a comment to what you said. Of course, there's another reason for making amplitude interference measurements, because then you have the phase information as well, so you can reconstruct the whole image.
Absolutely. Okay. So for those who did not enter, another reason for doing this experiment with amplitude is that the amplitude is a supplementary, the phase is a supplementary information, absolutely. But it was such a nice idea, the idea of Hanbury Brown-Twiss. So.
Very good. Well, let's thank Professor for